Last talk we discussed the concept of potential energy. What I want to do here is look at the two kinds of conservative forces that show up in this course. We'll obtain their potential energy functions and we'll include them in our energy conservation equation right here. So let me erase some of this and we'll start looking at it. The first conservative force that we'll encounter in this course is the gravity force, the weight. So the first thing I want to do here is to figure out what the potential energy function for the weight force is. Now we know that the force due to gravity, the weight, is minus mg j hat, where j hat is a vector along the y direction. So here's our normal coordinate system. Okay, so how do we know that this force is conservative? If you're far enough along in your calculus, you can check and convince yourself that this force has zero curl. If you're not, you can either trust me, or we can look at one of the other properties that we talked about last time. We said that if you have a force that's conservative, then the work done on a round trip equals zero. Let's think about that before we obtain this potential energy function. Suppose I have a baseball that I'm going to throw straight up in the air. This baseball has some mass and I throw it up in the air at speed v. Now it's going to go up this way, only gravity is going to act on it and it's going to come back down. We know from what we have talked about before that when the baseball gets back to the height it started from, it's going to be moving just as fast in the opposite direction. So suppose I look at the work done by the gravity force along this closed path. It begins here and it ends at the same place, so it's a closed path. The work done by all forces is going to be the change in the kinetic energy. Now, only gravity is doing work on this, so the work done by all forces is just the work done by gravity. And that's going to be kF minus ki, change in kinetic energy. Half mv squared at the end minus half mv squared at the beginning. Because the baseball has the same speed in the beginning as it does at the end, these two terms are going to be equal. And this equals zero. So over the round trip, gravity does zero work on this ball. It's important to notice that what this work and energy approach is telling us about is speed, not velocity. The ball has a different velocity at the beginning versus the end. Here it's moving up, here it's moving down. But the work and energy is telling us only about speed. The ball has the same speed here as it has here, and that's why this work done by gravity is zero. Because the work is zero on a closed path, the force is conservative. So I can come over here and be sure that if I evaluate the work done by gravity over any path I want, I'm going to end up with a scalar function evaluated at the initial point minus the same scalar function evaluated at the final point. And all I have to do here is figure out what that scalar function is. Okay, so let's do that, and we'll find the potential energy function associated with the gravity force. Now, the gravity force is constant. We have looked at this before. It's minus mg j hat. So when I drag it out of the integral, I end up dotting this into the displacement vector. So this is F times delta R. The displacement vector has two components, an x component and a y component. So let me write those. There's the force dotted into delta x I hat plus delta y j hat. When I do this dot product now, j hat dot I hat is 0, so the sideways motion doesn't matter at all. You can move sideways as much or as little as you want, and gravity will do no work because of that sideways motion. All of the work done by gravity comes from dotting this j hat into this j hat. And so you get minus mg delta y. The work done by gravity is minus mg delta y, which we can write as minus delta mg y. And that tells me the potential energy function. This is minus delta u, so this has to equal minus delta u. It's the work done minus delta u, I'll call it u sub g, the potential energy function for gravity. So we see that for gravity, the potential energy is mgy. And that's what gets used in our energy conservation equation. The energy conservation becomes the work done by other forces that we talked about last time, plus the initial kinetic energy, plus the initial gravitational potential energy, equals the final kinetic energy plus the final gravitational potential energy. All right, so when you're using the energy conservation equation and you come across this term, u sub g, it's the potential energy associated with the gravity force. It equals mgy, the object's mass, times 9.8 meters per second squared on Earth, times the height, y, that object is above or below some reference. You are always free, when you're calculating gravitational potential energies, to pick your reference level, to pick where y should equal 0. Usually we pick it on the ground, but it can be anywhere you want. The important thing when it comes to looking at how an object's moving is how that potential energy function changes. Its value relative to a reference doesn't matter. What matters is how it changes. When it comes to potential energies, it's always the change in the potential energy function that matters. Okay, so that's our first conservative force. It's the gravity force. When you want to solve problems including it, you end up with this gravitational potential energy, which is mgy. There's an initial value at the object's first location and a final value at the object's last location, and they are all relative to some 0 that you choose, usually on the ground, but it could be anywhere else. Let's look at the other one, and that has to do with the spring force. The second conservative force we'll talk about this semester is the spring force. So let me erase this and we'll look at springs. All right, suppose I have a spring that's attached to the wall right here, and I'm going to push or pull this spring. I'm going to displace it from its equilibrium position. Let's say that right here at x equals 0, the spring is at equilibrium. Suppose I want to stretch this spring out. So imagine we reach up here with our hand, we grab this spring, and we're going to stretch it out so that after we stretch it, the spring looks like this, and our hand is grabbing this thing. The spring is going to exert a force on our hand, and that force is going to be this way. So the spring force will be directed back towards the equilibrium point. If instead I had compressed the spring with my hand, the spring would be pushing the spring back to its equilibrium again. The spring force is an example of what we call a restoring force. That force is always directed back to the equilibrium location. If you stretch it, it pulls back. If you compress it, it pushes back. The force is always pointing toward the equilibrium position. If we write that as an equation, we model the spring force this way. The spring force equals minus k times x in the I hat direction. Now, this minus sign is what tells me this is a restoring force. If I stretch the spring to positive x values, this minus sign makes the spring force go in the negative x direction. If, on the other hand, I compress the spring over here, where x is negative, this negative times this negative gives me a positive force, and that tells me the spring force will be directed this way, along positive x, so that no matter what I do to the spring, the force is always going to point back to the equilibrium position. This is what we call Hooke's law, and it tells us that the spring force is proportional to the stretch or compression of a spring. The constant of proportionality right here is what we call the spring constant. In SI units, the spring constant has units of newtons per meter, and it tells you how strong or weak the spring is. If you have a very strong spring, it's going to have a large spring constant. It takes a large force to compress or stretch it some distance. If you have a weak, wimpy spring, the spring constant will be small. It takes a relatively small force to compress or stretch the spring a certain distance. So that spring constant tells you how strong the spring is, what force is required to stretch or compress the spring a certain distance. If we want to know the potential energy function associated with this force, what we need to do is evaluate the work done. And if this force is conservative, which it is, what we're going to find is that when we do this, we will end up with some potential energy function evaluated at the initial location minus the same function at the final location. So let's do that and see what we get. We're going to be moving in one dimension here, so this ds just becomes dx. We're going to move along the x-axis only. The spring force is minus kx I hat dotted into dx I hat, and we're going to move from some initial to some final x location. The minus k can be factored out, and the I hat dot I hat just becomes 1, so we end up with minus k integral of x dx from x initial to x final. And that is just minus 1/2 kx squared between these two locations. So that gives me minus the change in this quantity 1/2 kx squared. 1/2 kx squared is then the potential energy function associated with springs. So if I have springs in my problem, the way I would include them is to take the work energy theorem, which tells me the work done by other forces, plus the initial kinetic energy, plus the initial potential energy equals final kinetic plus final potential energy. And now I'm going to include the two kinds of potential energy that we know about. Potential energy associated with the gravity force and the potential energy associated with the spring force. So there are two potential energies here. Gravitational potential energy and spring potential energy, both at the initial point. And the same thing over here. This is now UGF plus USF. And if you want to write this thing out with all terms explicitly there, you get this very wide equation. Okay, so here it is. This is our final form for the energy conservation equation. And what it tells me is if we know the initial energies, there's two kinds, kinetic and potential, with there being two kinds of potential energy now. If we know those, and we know how much energy gets deposited or removed by work, then we know how much energy there is in the end. And this is the form of the equation that we'll use most often when there are springs in the problem. If a problem has no springs, then we can just leave off this U sub s term. and work with the shorter version of it. But those are our two conservative forces that we'll encounter this semester and the potential energy functions that go with them. Let me just write those down again so that we have them here. The potential energy function associated with the gravity force is mgy, and the potential energy function associated with the spring force is 1/2 kx squared, where k is the spring constant, tells you how strong or wimpy a spring is, and x is how far the spring is stretched or compressed relative to its equilibrium location. Okay, let's move into looking at some examples and problems now.